Okay, let's get the show on the road. And we're all excited to be back. See it in your eyes, we're all like, oh, I miss this so much. I understand. That's why we're having a quiz tomorrow as a welcome back gift. So remember quiz 9 tomorrow. It'll cover finding critical points. So make sure you know how to do that. It will cover the closed interval method. Right, this basically means finding absolute extrema on a closed interval. And it will cover the mean value theorem. You can also look at Rolle's theorem. Technically, the mean value theorem covers the case of Rolle's theorem. Pretty much, if you look at the mean value theorem where the average rate of change is 0, that gives you Rolle's theorem. But we sort of use Rolle's theorem to prove the mean value theorem. So make sure you remember that stuff for tomorrow. In the meantime, we are going to actually continue with a different topic altogether. We're starting to segue more into applications. So we're mostly going to start looking now at how derivatives are used. We know a bunch of ways to actually compute them, but now we are kind of going into how we use them. And the first excursion into such an enterprise will be 3.3. Textbook. This topic is on derivatives and the shapes of graphs. So at the moment, most of today I'm just going to be, we're not really going to do any concrete examples. There are some ideas and terms that I want to define for you guys and just talk about them a little bit. We'll more talk about their applications going into next class. Basically, when we're talking about the graph, we're talking about the picture of a function drawn on the xy plane. And usually this function would be something that you're tracking, something that you care about, and the shape of that graph could imply certain things about the thing that you're tracking, and that's what we're going to want to be able to talk about. We're going to want to talk about certain shapes that a graph might have, what they mean, and how can derivatives help us determine when or where such shapes or features will occur. So normally when you're looking at a graph, there are certain things you'd want to know about that picture, especially if it's representing something that you care about. You'd want to know where the graph is, or more specifically, intervals of. You want to know where the graph would be increasing or decreasing. Right? If you're tracking something, you'd want to know when it's getting larger over time versus smaller over time. You also tend to want to know where the extrema show up. Where does a maximum or a minimum show up on this graph? Right? This is usually something that you're going to be interested in because, let's say, just to throw an example out there, if you're drawing a graph that represents the profit that your company's making, then you'd want to know when would you hit a maximum profit, when do you have a minimum profit, what was going on relatively speaking around these times, for example. So you want to know when your profits are increasing, when are they going to hit a maximum, when your profits are decreasing, when they've hit a minimum, and you can use that to answer all sorts of questions. So extrema would be important. One thing that will also be important is the idea of concavity. Right, so that was on the bonus problem to the last quiz. We'll mention a little bit about that today, and I'll tell you what that means, as well as, this is sort of a subcategory of concavity really, something called an inflection point. Right? So these are some basic features of a graph, and they go along with certain shapes on the graph, and we can use derivatives to determine where these guys happen, assuming our derivative actually exists. Okay, so for the rest of this section, we'll assume that there's no breaks or gaps or jumps that we have to deal with, because those you have to kind of deal with on a case-by-case basis. We'll assume our function f of x, which I'm going to be using to illustrate things, is continuous on the intervals that I'm talking about. So now I just want to talk about some of these features. Let's start with the increasing and decreasing idea. Now this one shouldn't be too difficult to have a grasp of, because we've spent a lot of time on the first derivative, and we know that it means slope, and it's kind of intuitive what a positive versus a negative slope would mean in terms of increasing and decreasing, but I don't think we've formally written that down at any point, so we'll do that now. Definition. You say f of x is increasing on an interval if f of x2 is larger than f of x1 whenever x2 is larger than x1 for values inside that interval. i.e. f moves up as you go from left to right. Right? So whenever a function exhibits that behavior, we say it is increasing in that interval. So whatever interval it has that behavior on, we say it's increasing on that interval. So you have a graph, it's doing this thing, that's your f. If you pick an x1, you can get some y value at that point. Pick another value, an x value that's to the right of that x value, it turns out you would get a larger y value. Right? Whenever you have that happening, no matter which two x values you pick, we say the function is increasing in that interval. And another way to think of that, especially in terms of applications, you can kind of say as x gets larger, so does y. So whenever you have that kind of behavior happening, we say the function is increasing. And clearly, if at any point on an increasing function you were to pick a point in the interval where it's increasing and you were to draw a tangent line, you would notice that the tangent line will have positive slope. So this kind of implies that your f prime of x will be a positive number in that interval. So that's the first thing we want to talk about. So there's this feature of a graph that we call increasing. Increasing means as your input gets larger, your output will also get larger at every point in that interval. Picking successive x values where one x value is larger x values will always yield larger y values. We call this property increasing. And so now we can describe the property of increasing in terms of derivatives. So now we can say f is continuous then f prime of x greater than 0 on an interval I will to us be synonymous, it happens if and only if f is increasing on I. So in other words, if we want to figure out where a function is increasing, and of course we're assuming the derivative exists in this case. Assuming we can find the derivative, if we realize that in some region for every point on some interval, the derivative is positive, we can say the function is increasing on that interval. That's a very important property. That means that the function is moving up as you go from left to right, and you can describe that behavior in terms of a derivative, the first derivative, in fact. We can talk about decreasing. It's a very similar idea, as you could imagine. So let's just go through the motions here. F is decreasing on I if x2 is smaller than f of x1, or x2 larger than x1, where these guys are inputs in your interval, i.e. f goes down as you move from left to right. Y values for inputs to the right are always getting smaller. So that would mean the graph would look something like this, doing its thing. You can pick an x1 value, that will give you some corresponding y value. You pick an x value to the right of that, it will give you a smaller y value. And so that means as x gets larger, your y gets smaller. And you can, of course, imagine in this case, if you were to sketch a tangent line, your derivative, the slope of that line will be negative. Therefore, your derivative in that interval will be negative. And so we can say f is continuous, then a negative slope implies decreasing behavior. So conceptually, those shouldn't be too hard for us to grasp at the moment. But yeah, just to formally write that down, you can just assume that these two things will hold. F prime positive means you're increasing, F prime negative means you're decreasing. So that wasn't so bad. Let's move on to the next property, local extrema. We already know about absolute extrema. Let's actually talk about the local extrema at this point. So the closed interval method allows us to find absolute extrema. For local extrema, we can also talk about derivatives. And again, assume f is continuous on the interval. So we're kind of going to use our idea about increasing and decreasing to talk about when you might hit like a maximum or a minimum in the local sense. So let's talk about local maxes first. Now there are a couple kinds that we'd want to talk about. Assuming our f is always continuous, there's no hole or no gaps. A maximum can be one of two flavors. It can be something like this, where there's a sharp point. Right? We already know that the derivative would not exist at such a point. Or you can have something a little bit more smoother, where you have that kind of situation. Now, the indicated points here are, of course, the maximum in a certain region. And this doesn't describe all possible scenarios. These represent the two kinds of scenarios that we can discover, assuming our f is continuous and we hit a maximum. You would notice at this point, the derivative does not exist. We know derivatives don't exist at sharp corners. Where at this point, we have a maximum, and it's smooth enough for the derivative to exist. So Fermat's theorem would imply that the slope is actually 0. What you can start to realize then, when you start to actually chart these guys, let's say this point occurs at x0. What you'll notice is going to happen is that for this point to be a maximum, you'd have to be increasing to it, but then you can never pass it. So after you hit that point, you have to start decreasing, right? Whenever you're increasing towards something and then you start decreasing right after you hit that thing would have been your maximum point, right? So you'll notice that on the left side here, based on what we know increasing means, the derivative should be positive. And on the right side, we expect the derivative to be negative. Of course, at this point, you can see from these two flavors here, you can either be in the situation where your derivative is 0 or undefined, i.e. we have hit a critical point. And this would imply that you have a local maximum at x0. And pretty much, the same thing is going to happen here. Right? In this case, the derivative was undefined. In that case, it's 0. However, if our function is continuous and we're increasing on the left, decreasing on the right, and there's a point in between these two situations where the derivative is 0 or undefined, then that point will consequently give us a local maximum point. So if we zoom in on that point, y values to the left and right of it will be smaller than that point. Of course, a similar idea happens with minimum. So for local minima, a very similar idea will hold. So you can have a situation like this, or like that, just to kind of highlight the two sort of scenarios. So not exhaustive examples, just illustrative ones. And you'd realize that if you were to plot this point on the axis, what you have here is that your derivative is negative, you're decreasing towards a point. You hit that point and then you immediately start increasing from that point. Then that point would necessarily be the lowest point that you hit, and consequently our f prime will be 0 by Fermat's theorem, assuming the derivative exists. It will be undefined, assuming it doesn't exist. And so this would give rise to a local min at x0. And you can summarize this kind of thing in, of course, the data here. And you pretty much summarize this finding with something called the first derivative test. So this is a test by which Assuming our function is continuous, and we can actually, assuming our function is continuous, we can use derivatives to determine where local extrema happens. We call it the first derivative test because we're going to use the first derivative to determine this behavior. So this is to determine local extrema if they exist. So one, you would find the critical points. This is, of course, involves finding the derivative, because critical points occur when the derivative is 0 or undefined. You will test the critical points using the first derivative, and 3, you would conclude based on the following. So you sort of test them, in practice you would sort of test them the same kind of way you would test things when you want to solve an inequality. So on a number line, you apply x0, which is going to be your critical point, and you're plugging things into the first derivative of the function. So what you can do is you can pick a random point to its left, a random point to its right, and if f prime at x1 is greater than 0, while f prime of x2 is less than 0, this gives you a maximum. Conversely. If I find that critical point, take a random point to its left and to its right. Right, and of course I'm assuming no other critical points end up between these guys. Conversely, if my derivative evaluated at x1 is less than 0, and my derivative evaluated at x2 is less than 0, greater than 0, then that gives you a minimum. And this process is called the first derivative test. That's it. Find all critical points, you test them on intervals based on that. And you pretty much assume otherwise, nada. So you can identify a max and min using the first derivative via the first derivative test. And that was it. So we spoke about increasing, decreasing. And now let's talk about any questions on this first of all before we move on. How to do it, why it works. Now we're going to talk about something called concavity. But to really talk about this, I kind of have to talk about higher derivatives. But let's start with one definition, and we'll get to the other one pretty soon. We say f is, here's the phrase, concave up. On an interval I if the tangent lines always lie below f in I. So let's actually look at that. So there's a certain behavior that we call concave up. This behavior is defined as The behavior of a function where wherever you draw a tangent line, it will be below the function in that region. What would a function have to shape like for that to happen? Well, one possibility is that the function would shape like this. Another possibility is the function would shape like that, for example. Okay. You will notice here, I can plot points and pretty much draw tangent lines at every point here, and you'll notice that my tangent line is always actually below the function. I don't have one of those green lines cutting above the function here. Similarly, if I were to draw tangent lines at several points here, the same behavior would happen. Turns out that the white line is always larger than the tangent lines to the point. This kind of behavior is called concave up. Now, here's the question. What could you say about the slopes of the tangent lines? Yeah?
No.
Oh. If you were to not really focus on the function itself, but to focus on those green lines, and in particular look at the slope of those green lines, what would you say is happening to them? So what would you guess that this tangent line, the slope was here? Yeah, 0 is a nice, right? So you probably guess 0 is the slope. What would you guess it was over here? Some negative number, right? Let's say negative 10, whatever. What would you guess like over here? Negative 1, some other negative number. But notice that you intuitively wanted to pick a less negative number, right? Here it's very steep in the negative direction. It's getting less steep, still negative. Eventually it hits 0. We can kind of play the same game. Here, well, the function might increase, slope is, and just random numbers here, 5. If I were to say what the slope is over here, intuitively you'd realize that, hey, that's actually more steep than it was over here. That has to be something bigger. 15, whatever, right? What you would realize here is that the slope is increasing. In other words, if you thought of the slope as a function itself, it's getting larger as you move from left to right. Now, by above, what we were talking about earlier, slope increasing would imply what? Well, if we know if there's a function that is increasing, what do we know about the function? Its derivative is positive. In other words, the slope, saying the slope is increasing is saying that the derivative of the slope is positive. But we now know slope is actually itself a synonym for derivative. So if my original function was f, the slope can be described as f prime. And what I'm saying here is the derivative of f prime is positive. Now what is the derivative of f prime? Right? Now, definition. The derivative of the derivative of something when it exists is called the second derivative. It's called the second derivative. Okay? You take the derivative of a derivative, you say you've taken the second derivative. Now, it's worth mentioning that this itself does not always exist. There are functions that when you take their derivative, you can actually do it again. But we also know of a lot of functions where if you take their derivative, you actually can do it again, right? Look at x squared, the derivative is what? 2x. Y equals 2x is just another function, and it's differentiable, it's a polynomial. I could differentiate again, get 2. But y equals 2 is another function. I could differentiate that again. I would get y equals 0, right? So sometimes you can differentiate a function. The result is going to be some other function that you can differentiate again. And sometimes you get another function you can differentiate again, and differentiate again, and differentiate again. There are some functions, very nice ones, that you can actually do this forever. You can just, here are some nice functions that you can literally differentiate forever. Just find a derivative, find another one, find another one, find another one. There are some functions who don't behave that way. The functions that do behave that way are super important. Those are going to be the guys for which you can find what's called a power series. And you would talk about that in Calc 2. I will sort of leave it there. But functions that you can take derivatives forever are called power series. You can actually find power series to represent them. And it's not always possible, but sometimes it is. Whenever it's possible to take a derivative of something twice, you can say you found the second derivative. And at this point, let's actually talk about the higher derivatives. That's what they're called, higher derivatives. You basically think of these guys as derivatives of derivatives. And let's talk about the notation here. Let's do it over here. So we can talk about higher derivatives using what we call the prime notation. You know, the Newton's prime notation. You can also talk about them from the Leibniz notation. Here, I'm just going to say what we call in the name or whatever. Okay. So here, let's assume we have f of x. Here we call it y. Here we call it, well, it's the original function. Okay, so there are times when you can find the derivative of the original function. With the prime notation, you would call this f prime. With the Leibniz notation, you would call this dy dx. And this would be what we call now the first derivative. Right? Before we just called it the derivative, but you can emphasize that it is just the first one, the first derivative. But there are times when this itself is a function that you can differentiate again. And the notation for that guy is f double prime. That's how we say it. It would be called d squared y dx squared. In Leibniz notation, that's how you talk about the second derivative. It's called the second derivative. Okay. Sometimes you can actually, this is a function you can actually differentiate again. You'd say f triple prime d cubed y dx cubed. It's called the third derivative. And we can actually continue. Right? And BTW here. These notations come from the fact that we can treat the Leibniz notation as a fraction. So let's say you wanted to find the derivative of the derivative. Basically what you're looking at is you're taking d dx of d dx of y. So you can take this d dx and it becomes d dx squared, right? So here you have d times d, you get d squared. Here you have dx times dx. Remember, it's two letters, but it's considered one variable. So it's dx squared, and then you'd have the y just hanging out, right? And then you can apply another d dx, and you get d dx cubed, then d dx to the fourth, etc. So you can kind of continue this process here. What happens with the prime notation is that eventually it gets very annoying actually writing all these notches down, right? So once you get to the 20th derivative, you don't want to have to, right? Like someone's going to read that you're looking at the 20th derivative, they literally have to like count the little, damn, lost count. It's going to be very annoying. So how they usually do that is they put power in parentheses. So you can talk about something like the 15th derivative, right? So that would be f to the 15th in parentheses of x. Here you'd have d15y over dx15. Here you'd have the 15th derivative. And of course, in general, how this would look is like f to the n of x, dny, dxn. This is the nth derivative. It's worth mentioning, often we will actually think of the original function as the 0th derivative, right? That's the function when you took no derivatives. It's the original, right? It's called the 0th derivative. So there's a theory of higher derivatives here, right? So there are times when you can keep taking derivatives. Not always, but for many functions that we care about, you can. Polynomials, for example, you can. Trig functions, you can. You can take the derivative of sine of x over and over. You can take the derivative of the exponential function over and over. Take the derivative of the logarithmic function over and over. There are a lot of functions that we know of that we can actually keep doing this process. Okay? And another BTW is just to be careful with the notation. If you write that, that is of course y squared. Whereas if you write that, that means second derivative. Right? So it's another thing. So whenever you're reading a book or anything and they put the power in parentheses, you're like, what does that mean? This is what it means. They're actually talking about a derivative. So that's the notation. This is how we can describe derivatives. These are called higher derivatives when we're thinking of it this way. So we're looking at a function for which we can actually take derivatives over and over and over again. Okay. So that's just a notation that we can use. Let's go back and focus on the second derivative, because that's the guy that ultimately we looked at when we saw our graph had a certain shape. So back to the second derivative, right? That's what started this argument, but I just wanted you to know that it's a part of a larger universe. And that universe you'll explore a lot more in calculus too. But for now, back to the second derivative and what it can tell us about a graph. Right? So we saw, if you were concave up, quote unquote, that refers to a shape like this, where the tangent line is always below the function. And so we saw concave up happens precisely when the derivative of f prime is positive, but we now know we can actually have a name for that. We call this the second derivative. So we can now say the following conclusion. F is concave up on I. If and only if its second derivative is positive on I. Of course, we're assuming existence here. Okay. So we're assuming our function is continuous. It's just continuing to do whatever it's doing, and we want to talk about a certain kind of shape that we call concave up. And we can determine when a function is concave up by looking at the second derivative. So I find a derivative, and then I find the derivative of that result. If I figure out where that guy is positive, I can determine where a function is concave up. And by the way, there's a mnemonic that goes along with this. It's called concave up like a cup. Right? So what the important thing I want you to get is the following. Concavity is about shape. Right? It doesn't matter if you're increasing or decreasing, that is not what you look at the second derivative for. Right? You can be here, here's a function, it's increasing and concave up. Here's an example of another function. This one is decreasing and concave up. Concave up is not about increasing or decreasing. It is literally about the shape you take while you might be increasing or decreasing, right? So it's when your function is bent like this, like a cup. You can hold water in it, right? So you say concave up like a cup. Now it turns out the opposite is also going to be very intuitive. There is such a notion called concave down. That would be concave down like a frown. Okay? So you can talk about concave up, you're happy, you're smiling, you're feeling positive, everything is concave up. Or you can be concave down. You're negative, feel down, you frown. That's when you're sort of curving this way. So you can talk about a function that's bending like this while it's doing whatever it's doing, and whenever a function is doing that, you can say, oh, it's concave up, right? If a function is bending like this while doing whatever it's doing, you can say, oh, the function is concave down. And what this kind of bend means is that the slope is increasing. In particular, what this will mean is that this is the behavior that a function will take when it's increasing, but it's increasing faster and faster and faster, right? However fast it was increasing now, in the future, it will be increasing by even more, right? If it's concave up and decreasing, this says, okay, we have something that's decreasing, but it's decreasing slower and slower. However much it's decreasing now, in the future, it's going to be decreasing, but by less. Okay? So you can start to talk about not only whether something is increasing or decreasing, whether it's getting larger or smaller, but you can talk about the rate of the increase or the rate of the decreasing. Is it decreasing by more and more, or by less and less? Or it could possibly be decreasing by a constant amount, right? In which case you'd have like this, right? In which case you wouldn't have a concavity because your second derivative would actually be 0 there. Because the derivative of a straight line would be a constant, the second derivative would therefore be 0, which it wouldn't be either concave up or concave down, right? So concavity is really talking about these two kind of behaviors. The smiley face, up like a cup, or the frowny face behavior, down like a frown. It's talking about the shape. And that shape can imply several things. So next time I'm going to write down what concave down means, like give you this, because I didn't write it for my other class, so I'm not going to write it for you guys. But we actually stopped there. And I will see you guys tomorrow. We'll continue this discussion. And we'll do some examples of this when we get to curve sketching. Yeah. Come again? Yeah, this stuff. Yeah, any stuff from... Well, no, I think our quiz covers everything we did before here. Mean value theorem was the last thing we did. Yeah. So it covers this stuff. So you can know about the second derivative, concavity, increasing and decreasing.
The concavity means the derivative.
Huh? To be able to determine the concavity, yeah, you